Well, hello once again, AP Calculus students. We're looking today at the topic of continuity. That came up actually when we were dealing a little bit with the limit of a composite function. Recall the inside function limit had to exist, and then the outer function had to be continuous at x equals k if k was the limit of that inner function. And then the composite function, of course, that limit was just f of k. As its value. So let's see if we can't then get a little idea of continuity. We first of all talk about continuity at a point and then expand that idea. If it's continuous for each point on the interval, then the interval is said to be continuous. So we're looking today then at the criteria for continuity, and then looking at also discontinuities, where or what type of discontinuities exist. And then if indeed we can maybe perhaps make the function continuous a little bit, that is a special discontinuity. So anyway, let's get into this. For the criteria for continuity at a point, the function has to exist at that point. The limit has to exist at that point, and then they have to be the same value. So whatever the function value is equal to the limit. You might write it like this, that f of x, if x is the point, or let's even, x is a little bit too specific maybe. Let's specifically talk about some point c. F of c is equal to the limit as x approaches c of f of x. If that's the case, then the function is continuous at that point. So I write that just a little different. Basically, the idea, and I think you'll see what I basically have to be able to show, that the left-hand limit equals the right-hand limit, which therefore the limit exists, and then has to equal the function value. So on the AP test, I might encourage you to write something like that if you were trying to prove that a function was continuous, that you recognize both the left-hand limit and right-hand limit are the same, and then as well it's equal to the function value, and therefore it is continuous at that particular point. And once again, if it's continuous at all points on the interval under this criteria, then the function is said to be continuous on a particular for that entire interval. So looking at some discontinuities, there are two different types, removable and non-removable. And the removable ones is where you have a hole, typically where the functions agree at all except one point perhaps. But indeed, if it's removable, you can redefine the function at that particular point to make it continuous. And then a non-removable discontinuity is either a jump discontinuity or perhaps a discontinuity at an asymptote, typically a vertical asymptote. So in these three examples, first of all, let's talk about why these fail to perhaps be continuous, or and then also determine what kind of discontinuity it is if it's not continuous. So in this case, the limit appears to exist, whatever this y value is here. The limit exists, left-hand limit equals right-hand limit, but the function's undefined, so therefore is not continuous at f of c. And then I'm going to skip over to 3. Again, the limit exists, appears, whatever y value that point is. The function exists, some y value down here for f of c, but they're not the same. So again, it's not continuous. 1 and 3 are cases of removable discontinuities, because I can redefine the function where f of c perhaps, excuse me, I can redefine the function such that f of c, if f of c were this value, then it would be continuous. and I can redefine in problem 3 the function to be this same as the limit, and then it would be continuous. So if I could do that, then it's a removable discontinuity. And if I do that, it's typically done in a piecewise function. You'd see that maybe come up. So let me erase those a little bit, because I don't really want to consider that as necessarily always the case. In 2A, I have a jump discontinuity. It is there, the limit doesn't even exist. The function does exist. It does have a function value, but the limit doesn't exist. Left-hand limit's not equal to the right-hand limit, and therefore it's not continuous. You cannot redefine a particular point to make that continuous, and therefore it's then a non-removable discontinuity in 2A, and particularly a jump. Those two removable. And of course, I have a vertical asymptote in 2B. Again, the limit doesn't exist. Left-hand limit and the right-hand limit, we haven't talked about this yet, but it's coming up in the next section. We don't say that the limits are infinity. We actually say that the function is infinite at that point. But again, the limit doesn't exist at 2B, nor does even the function have a value at f of c. So double whammy on that one. But again, here's the case of an asymptote. Vertical asymptote at x equals c. All right, so I had also another problem I took from the notes. We want to look at a couple special limits and see what intervals perhaps I could say that this function is continuous for. And usually on continuity, you're never wrong if you put open intervals. You could include closed intervals. However, if you miss a closed interval when it should have been open, you'd be taken off. If you put down an open interval when it could have been closed, you won't be taken off for those points. So I would suggest to you to make sure you realize what you're doing there. So let's look, first of all, these 4 different limits. As x gets close to -1 from the left, and as x gets, the limit appears to be 1. As f of x gets close to -1 from the right, the limit 0. Left-hand limit not equal to the right-hand limit. Therefore, the limit does not exist at -1, nor could it be continuous then. And in particular, again, hopefully you're recognizing that would be a jump discontinuity. And as x goes to 1, left-hand limit is infinite, right-hand limit, the function is infinite. So again, those are the same. However, I don't say that the limit isn't, well, technically I will say eventually that that limit is infinite as x goes to 1. Not infinity, but the function is infinite at that point, x equals 1. That comes up in topic 3.8 when I come back and revisit asymptotes again. But, and we were going to go ahead and just, that's the way we'll talk about it later. So we're going to go ahead and just say that that is infinite at this point. As x goes to 3, left-hand limit equals the right-hand limit and is equal to 0. And as x goes to 5, however, let's go back here again to this one. This, of course, is an asymptote. The limit exists at x equals 3, and the function exists at x equals 3, but they're not the same. So it's not continuous, but it is a removable discontinuity. And then as x goes to 5, the limit exists, the function does not. Again, it's the limit appears to be 2, left-hand limit, right-hand limit. And again, the function doesn't exist. So again, it's not continuous. it is a removable discontinuity. I could redefine the function for f of 5 to be 2, and then it would make it continuous. And therefore, again, it's a removable discontinuity. So that'll hopefully will maybe clear up a few things about continuity and discontinuities in those notes. We'll next time look at vertical and horizontal asymptotes in our next video. And but for now, then this will be it. And so take care of yourselves, and we'll see you again next time. Bye.